in Theoretical Computer Science, organized by the Department of Computer Science and Engineering in association with the IIT Drishti. This is our second winter school, and I'm happy to see some of you again this year. Last year we organized a 2-week winter school, but this year because of upcoming AI and TCS conferences next week in India, we just planned a mini school. So, but I'm happy that you joined us even for the small event. So, I would like to share that our list of participants is quite diverse. We have UG students, PG students, PhD students, and even faculty members, not just from India, even from abroad. So we have some participants from Israel. I'm very happy that they somehow managed to come. And you can see that our participants are from IIT Pune, NISER, IITs, various universities, IIT Bhopal, Anna University, CIT, IIT, IIT and many more, you can see, right? And it's not just the participants, even our list of speakers is also quite diverse. So we have speakers from University of Glasgow, Professor David Manlock, Tata Institute of Fundamental Research, Professor Kavita, Institute of Mathematical Science, Professor Sushmita Gupta. From IIT Hyderabad we'll have Professor Charu Sharma, and of course some of our ITG faculty. So most of these speakers will be present here in person. Professor David won't be able to join us in person, but all the other speakers are here. Professor Sushmita is already here. Professor Kavita will be joining us tomorrow, and Professor Charu will be joining us, I think, on 11th. So I would like to encourage you all to interact with the speakers and your fellow participants. Believe me, this is a very good opportunity to build network. You may find friends, collaborators, your mentors, your host, future host, and there are many more opportunities. So do utilize. And this is Jodhpur, wonderful, I would say wonderful month to visit Jodhpur. So please do explore this city as well. And I hope you are already enjoying our campus. So we are delighted to have you all, and I won't take too much time. I would, for the formal inauguration event, I would like to invite our HOD, Mr. Gaurav Harith, to address the audience. Thank you.
So welcome all the participants to IIT Jodhpur. So thanks to the untiring efforts of the organizing team that you all have been here. They have been working on it for the past few months, and I've been part of the mail chains for every kind of arrangement that they've been making for you people for a comfortable trip and for a nice event. So AI and theoretical computer science both are one of our thrust areas. We have several thrust areas on security, networking, and cyber-physical systems. So these two thrust areas are also there, and we offer them as specializations for our undergraduate and the postgraduate students also. And these group of faculty members who are part of these areas, they are quite excited to share their in-depth expertise to you all in the form of this kind of a workshop. And we also benefit from these workshops. Department benefits because it strengthens our collaboration with the peer institutes and the industry. And with the exchange of ideas, we also get to know of new problems to work on, and that in turn strengthens our thrust areas also. So thrust areas are quite important, like everybody has interests, and it's your interest which gets you along and make friends with others. So just like that, institutes need to be part of some academic ecosystem, and they need good thrust areas to work on so that they can also build up friendship with other institutes. So we all need to upgrade our skills every now and then, because you see that the technology is changing very fast. The new generation technology comes in a matter of few months, okay, not just generations or decades. So we need to update ourselves, we need to upgrade our skills, and to do that, we need to exchange our ideas, exchange our thoughts in the form of these kind of forums. And I hope all of you are going to make good use of the interactions which you will have amongst yourself in this piece. So with this, I would like to welcome all the speakers, eminent speakers for this event. And I would like to also welcome you. Hope you have wonderful next 4 days in this AI plus theoretical computer science workshop. It's a very interesting thing because ultimately every invention of AI has some roots in theoretical computer science. You will take, let's say, John McCarthy. He's the father of AI, and he was the one who discovered, invented multi-programming. That is, your CPU is able to switch its work on multiple processes at the same time, so that kind of switching. That was his idea. But ultimately, he was also doing a kind of optimization for the knapsack problem which he applied to make computers more efficient, optimize the performance of the system. So every now and then we are basically rediscovering some aspects of theoretical computer science, and they become so relevant in AI that they lead to a new generation AI technology. So I think that's a very, very apt topic which the organizers have chosen for this year's winter school. So wish you all the very best, and welcome, and hope you will enjoy the next 4 days. Thank you.
Thank you, Professor Hare. So we will start with our first track, COSCOE, from today, and this is a 3 days event, and on 11th and 12th we have 3 division sessions. So we'll quickly introduce the COSCOE school. So I would like to invite Professor Sushmita Gopla to introduce the school, what all they are going to do and what all you can expect from this school. Thank you.
Thank you so much for showing up, all of you. I see many familiar faces who came last year, and I was very privileged to join last year as well. So continuing this tradition, this winter school, well, I have to say that I am noted as one of the organizers. I didn't do any of the organizing work. Everything was done by the IIT Jodhpur faculty members and staff, so all the credit goes to them. And, okay, so without much further ado, let's start by talking about what is this whole workshop, a sort of small mini school about. So it's titled as something to do with matching under preferences. So anybody has any idea what matching under preferences is?
Stable managed problem.
That's one problem, but what is this? What is more generally matching under preferences? So okay, so let's take a step backwards. If we look around us, we'll see lots of instances where basically we are trying to match things with other things. The things could be people, agents could be human beings or machines, and resources could be animate or inanimate objects. So these are terms like items, resources, these are just abstractions of stuff that we see around us, right? And while we understand, so what does matching means? It's basically just assigning things to things. Now the difference here is the goal is not just to create any such assignment. In most, if not all, real life applications, there is this idea of some things make more sense than the others, some assignments are more compatible than the other, and so on and so forth. So how do we capture these solution concepts, which are just not just a matching, but something more than that? That's what is studied under this umbrella term of matching under preferences. So if you see, this is like a collage. I try to create a collage of stuff, of interesting pictures related to some of the most well-known topics under matching under preferences. So one of the most well-known examples of matching under preferences is matching university students, like people who are applying to join universities, to available seats. You guys, all of you who came through the central entrance exam, be it the ISAs, IITs and so on and so forth, you all sort of came through a centralized system like that. You appeared for an exam, a ranking was brought out, then you showed up for counseling and chose a seat that was available. That is the one that you liked the most among those that were available. So that's like creating a matching which is sort of respects the preference, the ranking order of the students as well as the students' preference. Originally, this whole problem started out by us trying to assign medical interns to hospitals. So that's where in many parts of the world this still continues to date, and this is a very important setting in which matching under preferences is used. Roommate setting, well, maybe not in India, but abroad, you get to choose somewhat, have some say on who your roommate will be in university dorm rooms. So there is no guarantee that you'll get to room with your best friend, but the point is that you express your preference and then they try to come up with a sort of assignment to dorm rooms based that respects those preferences. Okay, and of course, perhaps the most socially relevant, useful, benevolent, altruistic application of matching under preference, at least in the past, used to be in kidney exchange networks, where a compatibility is obviously an imperative here. You can't just, I would be willing to give somebody an organ, somebody is willing to receive, but it just does not work there. Compatibility is a very strong sort of criteria here. So this is why it's more than just matching, it is matching under preference. Now, as you can see, all these situations that involve resource allocation, that respect preferences, they are not all identical. There are lots of other nuances and intricacies there. So therefore, studying it via just one problem, like he said, stable matching, does not quite help. That's the canonical, yeah. So that is the canonical solution concept in this area, but we have gone well beyond that in the many decades since it was first introduced. So in this school, that sort of is the goal, to introduce you all to some snippets of these solution concepts, these ideas, this mathematical formulation and so on. So, okay, I'd be remiss to say the importance of stable matching in real market scenarios really cannot be overstated. The importance of it was actually sort of recognized by a Nobel Prize in Economics in 2012, given to Alvin Roth and Lloyd Shapley. There's a typo there, the name Lloyd. And unfortunately, by then David Gale had already passed away a few years ago, so he was not one of the recipients. And the commendation stated that this was given for the theory of stable allocations and the practice of market design. So the objective of this school, as I said, was to introduce you all to some go beyond the stable matching or the stable marriage setting and introduce you to more generalized notions of stable matching, as well as give you the underlying theoretical and mathematical formulations by which we analyze these problems. Now, there is a whole host of researchers, an entire research community that sort of dedicates its effort towards studying these things from an empirical and economic point of view, sociological point of view, and so on. So we don't sort of look at the objective of the school, I mean, that's not our expertise, right? So we will start today's technical session by basically delving deep into the mathematics of stable matching. Follow that, we will look into the more generalized setting of the roommates, stable roommates problem. So what's the difference? The stable matching classically was studied in what we understand to be bipartite graphs. Or more originally, it was called, it was formulated as a study of two-sided markets. So employers on one side, employees on one side, because the role of employers and employees is very clearly stated. Employers are not going to become employees, employees don't suddenly become employers, so that's why bipartite graph is a natural way of formulating this scenario. The roommate setting does not have this two-sidedness. Everybody is a student, everybody is trying to get a sort of a dorm room and so on and so forth. So that's why these have very colorful terminologies. I mean, at least you have to give them full credit for creativity, and we'll see a few more sort of names such as this. So that's a roommate setting. It's just stable matching in arbitrary graphs. So now you might know, I think you were asked to study the Gale-Shapley algorithm, and so you might know some properties of it. One of the limitations of a stable matching solution, at least the Gale-Shapley algorithm, is the solution it creates is very one-sided. It benefits one side and not the other side, right? So naturally, one thing to study here would be to find a stable matching which is somewhat balanced, like which is fair to both sides, does not penalize one for the, at the behest of the other. So this is where the fairness notions comes in. Now what exactly would be an appropriate fairness notion in all scenarios cannot be answered. So it's very situation specific, and therefore there are different kinds of objective functions that are added on top of the stability constraint. So if you think of it from a mathematical programming perspective, it's like you want a stable solution, additionally you want it to maximize or minimize some objective criteria. Another generalization of stable matching is popularity. Now Kavita will give the talks on popular matching, but I can just say this very briefly, that stable matching is also a popular matching. So rather, what is popular matching? It's a matching which is at least as popular as any other matching in the graph. Where, how do we know what does popularity even mean in this case? It's like the vertices act as agents and they get to compare two solutions. I like my outcome in this matching versus that other matching. So if I have the exact same outcome in two matchings, then I'm basically agnostic. I don't care. I'm indifferent. But if I have different outcomes in different matchings, in two matchings, then I can sort of express my sort of preference over which matching I like based on the preferences that I had initially considered. So that's where, and then you do a vote counting of the number of voters or agents who preferred one matching and the number of agents that prefer the other matching. Whichever matching has more votes in favor is the more popular of the two. So this is the notion. So popular matching is one which is as popular as any other matching. So popular matching is a generalization of stable matching, because stable matching is also popular, and you'll see a result today which basically hints at that. But popular matching, the advantage of popular matching is it can have a size much bigger than what a stable matching can be. So stable matching has a very strong size limitation known as the rural hospital theorem, which says that in a given instance, preference, as long as the preferences are strict, every stable matching will have the exact same size. So and moreover, the same agents will get matched in every single stable matching. So basically, if you don't get matched in one stable matching, you are not going to get matched in any other stable matching. So that basically, on one hand, that's a very strong robustness condition in favor of the Gale-Shapley algorithm, right? But at the same time, it also says that the possibilities of matching as many agents or resources as possible is kind of a sort of a dead end. Now, of course, in a market scenario, in real life economic applications, leaving resources unmatched is a waste, and we don't want that. So the goal is, along with having stability, is to also have to match as many resources as possible. This is where popularity comes in, because a large maximum size popular matching can be in some instances twice as large as a stable matching can be. So that's why people study popular matching. Fractional matching. Now, the examples I gave over there, we were talking about one single resource being assigned in entirety to one agent, right? There is no fractionalizing. However, fractional matching can be thought of as like a mathematical framework which allows us to state the same stable matching problems in a different term is a mathematical programming formulation. And using the vast toolkit of that setup, we are able to answer questions that up until that point may not have been answerable using our combinatorial setup of graphs, vertices and edges. Along with the fact that fractional matching further generalizes the idea of matching items to agents, where basically now you're allowing an item to be as if split into pieces and being assigned like bundles of stuff to people such that some other compatibility notion and so on are satisfied. So it's both a generalization as well as a way of thinking where a problem can be solved in the fractional setting and reinterpreted in the standard integral setting. And then finally, as I started by saying, why do we want to go beyond stable matching? It's because size is an issue. You don't want waste. But as I said, the rural hospital theorem says that a stable matching cannot go beyond this. So there's a trade-off. You lose in stability but gain in size. And there are lots of results pertaining to this flavor of work, where how much can you, like how many blocking pairs do you need minimum so to increase the matching by a certain number of edges, for instance. Now beyond this, there are far too many topics on stable matching and related scenarios, and there are excellent textbooks, surveys and so on and so forth. Two outstanding textbooks, the one that I will be using is by Gusville Irving. It's called The Stable Marriage Problem. I couldn't find a screenshot of that, else I would have put it here. And the other one is a sort of a handbook by David Manlove, one of our speakers today, called Algorithmics of Matchings Under Preferences. Now finally, I end by saying, and this is a separate slide, is because we'll have, David's talk will be about kidney exchanges, in particular modern algorithmic techniques to actually find kidney exchange networks. Now, as I said, this can be modeled and used to be modeled as stable matching scenarios, but in recent times, like by recent time in several decades now, it has been looked at from mathematical programming perspectives for reasons you will hear from David. So this sort of fits into our theme of matching under preferences from historical perspective, and because how cleanly it captures the idea of matchings need to respect some constraints. The type of matching we are looking at need to be compatible, need to be on demand, like you can't just match anything to anybody. But the nature of the results and the discussion would be significant, sort of different from what we see for in the other talks. So with that, I think we can start our technical part, right? Thank you. Dick.
Now we have 5 minutes break and we start our technical sessions from 10:05. Thank you.